Imagine you are standing in a perfectly dark room. You reach for a light switch, but exactly a fraction of a millisecond before your fingers brush the plastic, someone else turns it off. In software engineering, we assume code executes in a perfectly logical sequence. A computer finishes step 1, then seamlessly moves to step 2. But problems arise when modern applications have to process 1,000 identical commands at the exact same microsecond. Consider a standard joint bank account shared by you and your partner. You open your app and check the balance. The screen clearly reads $100. At that exact microsecond, both of you tap to buy a $5 coffee. Two separate commands execute at once, and suddenly, perfect sequential logic breaks down. Two parallel timelines hit the same server simultaneously. Both read the initial $100 balance. Each independently subtracts 5, arriving at 95. Finally, both push their result back. The first writes 95, and instantly the second overwrites it. The localized math checks out, but the final outcome is a disaster. You and your partner just spent $10 total, yet the bank only deducted 5. This specific vulnerability is known as a race condition. It occurs when two invisible threads compete to read and write over the exact same piece of memory at the exact same time. The data was completely corrupted, but not by a bad formula. Time itself introduced random chance into the equation, destroying the mathematical integrity of the system. To understand the fix, we have to look beneath the sleek user interface, down to the raw CPU threads, actively fighting for that single block of memory. For decades, developers relied on a brute force method to stop these collisions. They built complex manual locks into their code. A lock acts as an aggressive gatekeeper. It completely blocks all other threads from touching a specific piece of data until the very first thread finishes its job and leaves. But as apps grew, these locks created massive bottlenecks. If a thread forgot to release a lock, or if two threads mathematically locked each other out, the entire application would freeze permanently. Treating every piece of shared data like a highly secured vault is incredibly inefficient when you are managing massive, multi-threaded environments. Apple introduced a far more elegant solution in Swift, designing an architectural structure specifically built to replace manual locks: actors. Think of an actor as an isolated island. By definition, it guarantees that only one thread can step onto the island and interact with the data at any given time. When we look at the Swift implementation, we see the await keyword. This explicitly tells the system that if a thread wants to modify the bank balance, it might have to pause its execution and let other processes run. Instead of crashing into each other or freezing the entire app, incoming commands automatically form a polite, orderly queue outside the actor. Swift actors remove the chaos of simultaneous requests entirely. They enforce a predictable, serialized timeline without the developer having to manually micromanage the server traffic. Major tech companies spend millions of dollars rigorously hunting down these microscopic overlaps because a single thread collision can compromise an entire database. In high-stakes financial environments, like a stock exchange executing thousands of overlapping trades per second, a race condition means creating or destroying money out of thin air. The exact same vulnerability applies to complex logistics networks. Without strict thread isolation, an airline database could easily assign the exact same seat to 3 different passengers simultaneously. When developers optimize the applications you rely on every day, they are doing so to guarantee absolute mathematical truth for millions of users actively tapping their screens at the exact same moment. By organizing shared data into isolated structures, engineers no longer have to chase unpredictable shadows through their code. With Swift concurrency and actors, time goes from being a destructive enemy to a completely controlled variable.